Yeah, so hello everyone. So today we are going to study some orbital mechanics and basically orbital motion. So just let me get back to my whiteboard. Mhm. Why does it say that I have no internet connection with me? I'm so sorry today. I'm having a bad throat, so I hope you bear with me on that. The whiteboard's opening, and yeah, we've got that. Okay, thank you. So in today's lecture, we are going to explain conceptually how an object is put into orbit, describe how to analyze the motion of any object. Okay, for example, let's take an example of a ball, of a tennis ball, and we throw it. Okay, so what type of motion is it going to follow? So what is an orbit? We said that it is type of a racetrack in space that the object drives around. But what makes these racetracks? Throughout the rest of the tutorial will explore the physical principle that allows orbits to exist as well as mathematical representation of them. But before diving into a complicated explanation, let's begin with a simple example experiment that illustrates conceptually how orbits work. To do this, imagine that we gather a bunch of baseballs to travel travel to the top of a tall mountain. Sorry for my throat. Visualize that we are standing on the top of a mountain. Let's say, visualize we are standing on top of a mountain. Okay, and prepare to pitch baseballs to the east. As the ball sails off the summit, what do we see? Besides seeing unsuspecting hikers planting up their trail and running for cover, you should see that the balls follow a curved path. So see, I throw it, it could go like this, it could go like this, it could go like this. Okay, and why is this? Because the gravity is pulling them down. Therefore, the compromised shape of the baseball path is a curve. Okay, B1, B2. Today my tab is working much better. I don't know why. The faster we throw the balls, the farther they go before hitting the ground. Okay, so if we initial increased, then this implies that the landing is increased. Distance of landing is increased. Hitting the ground, and this could lead us to conclude that the faster we throw them, the longer it takes before they hit the ground. Also, if vi is more, this implies that t landing is more. uh, as we watch two baseball players standing off a flat ground will release baseballs, the first one simply drops the ball from a fixed height like this. At exactly the same time, the second player throws an identical ball horizontally at the same height as hard as possible. So, like this. Okay. What will we see? If the second player throws a ball fast, it will travel out about 20 meters or so before it hits the ground. But the ball dropped by the first player will hit the ground at exactly the same time as the pitched ball. Wow, that that's amazing. So for example, if I drop something from here and I throw something as hard as possible, so it will go something like this. I mean, sorry for my bad, it will go something like this. Or, uh, yeah, okay. And the time of flight for time of fall, T1 and T2, are equal. T1 equal to T2. uh, so and it will follow, and this distance, let's say this is 20 meters. uh, uh, but the ball dropped by the first player will hit the ground at exactly the same time as the pitched ball. You see, how can this be? Yeah, how can this be? To understand this seeming paradox, we must recognize that in this case, the motion in one direction is independent of the motion in another. Yeah, exactly. See, what we are having here is uh, when the ball is moving in a projectile motion, it has got its motion in this direction and in this direction. So the forces that is acting, the components, the phenomena that is acting, that's pulling it down is pretty much the same as this one. So uh, it makes no difference to the vertical component of the ball. So this ball is having two components, one that is taking it forward and another that is taking it downward. So we now we understand that the motion in one direction is independent of the motion in another. Thus, while the second player's ball is moving horizontally at say at 30 kilometer per hour or so, it's still falling at the same rate as the first ball. Okay, so if I drop something, simply drop it, or if I throw something, okay, they will reach the ground in the same time. T1, T2. Okay. The rate is, and what is the rate? The rate is the constant gravitational acceleration of all objects near Earth's surface, and that is 9.798. 9.798. Thus, they hit the ground at the same time. The only difference is that the pitched ball, because it also has a horizontal velocity, will travel some horizontal distance before intercepting the ground. Okay, so but they are going to hit the ground at the same time. Okay. uh, Now uh, so you can see with the example, both balls hit at the same time. A dropped ball and a ball thrown horizontally from the same height will hit the ground at the same time. This is because horizontal and vertical motion are independent. Gravity is acting on both balls equally, pulling them. Is the recording on? Yeah. Pulling them uh, pulling them equally with exactly the same acceleration of motion. Now let's return to the top of our mountain and start throwing our baseballs faster and faster to see what happens. Okay, let me show you interesting image, some interesting images. Uh, just see it from here. You see, uh, one guy is simply dropping the ball, another is throwing it, but still they will hit the ground at exactly the same time. Now let's pan and move. Now let's return to the top of our mountain and start throwing our balls faster and faster, okay, to see what happens. No matter how fast we throw them, the balls still fall at the same rate. However, as we increase their horizontal velocity, they are able to travel farther and farther before they hit the ground, right? Because Earth is basically spherical in shape, something interesting happens. Earth's spherical shape causes the surface to drop approximately 5 meters vertically for every 8 kilometers, or for every 8 kilometers horizontally. So, Earth's spherical shape uh, makes Earth's spherical shape causes the surface to drop approximately 5 meters vertically for every 8 kilometers horizontally, as shown in figure 4.4. So yeah, let me show you that beautiful picture. Earth's curvature means Uh, Curvature means the surface curves down about 5 meters for every 8 kilometers. So if I go horizontally 8 kilometers, it means from my previous position I've actually dipped 5 meters. So we see it is not uh, as we all know, Earth is not a flat plane, it's spherical. Earth's spherical shape causes the shape to drop 5 meters vertically for every 8 kilometers horizontally, as shown in figure. So, if we were able to throw a baseball at 7.9 kilometers per second, assuming there is no resistance, its path would exactly match Earth's curvature. Okay, so actually, that is how we find out what is the first cosmic velocity of any spacecraft that is in Earth's orbit, and we'll get to that in a while. Its path would exactly match Earth's curvature. That is, gravity would pull it down about 5 meters for every 8 kilometers it travels, and it would continue around the Earth as a constant height. If we forget to tuck, it may hit us back. If we forget to tuck, it must hit us on our back. And let's see that with another example. See, uh, we throw a ball. We throw it a bit slowly, so it goes and hits somewhere on the earth. We throw it a little bit fast, it might end up in a circular orbit. We throw a little bit more fast, it might end up in a elliptical orbit. A little bit more fast, parabolic orbit, which means it goes like this and goes away from the sphere of influence. Hyperbola orbit, it means it leaves the earth. Yeah, it does not come back. In a parabolic orbit, it goes around the earth and then it leaves, but in a hyperbolic orbit it just goes away. So if we can throw anything of the earth at a speed of 7.9 kilometers per second, this is not meters per second, it is like reaching if you're in Bangalore, uh, reaching from, I don't know, A position to B position in something that's 8 kilometers apart in 1 second. Uh, okay, that is gravity. Would pull it down about 5 meters for every 8 kilometers it travels, and it would continue around the earth at a constant height. If we forget to duck, and yeah, exactly, if we forget to duck, it might hit us on the back. Okay, a ball thrown at a speed slower than 7.9 kilometers per second falls faster than earth curves away beneath it. Thus it eventually hits the surface. So yeah, we need to throw things faster than the earth curves. So the earth is curving 5 meters for every 8 kilometers. So so the earth is curving 5 meters for every 8 kilometers, so like this, for every 8 kilometers is dipping 5 meters. So if we have to put anything into an orbit that makes it overcome these constraints, that should be the speed, and we'll get to find out how do we get that speed. Thus it eventually hits the surface, and the result is that a ball throwing experiment is shown in figure 4.5, as I have already shown you. If we analyze our various baseball trajectories, we see a whole range of different shapes. Only one velocity produces a perfect circular trajectory. Slower velocities cause the trajectory to hit the earth at some point. If we need to project the shape through the earth, we'll find the trajectory is really a piece of an ellipse. It looks parabolic, but it's actually elliptical. Throwing a ball with a speed slightly faster than a circular velocity also results in an ellipse. If we throw a ball too hard, it leaves the earth altogether on a parabolic or hyperbolic trajectory, never to return. And that's how deep space missions are launched. No matter how hard we throw, our trajectory resembles either a circle, ellipse, parabola, or hyperbola. We'll all see this. These are all shapes of the conic sections. Okay, so an object in orbit is literally falling around the Earth, but because of its horizontal velocity, it never quite hit it. Because of the horizontal velocity throughout, so anything in orbit, it tries it tries to fall back. It tries to fall onto the earth, but before it's able to fall, the earth curves. So it tries to fall back again and again and again and again and again, and this keeps on happening, and that's how we end up in orbit. Okay, so it's moving faster than the earth curves. So and now we analyze motion. Now that we have looked at orbits conceptually, let's see how we can analyze this motion more rigorously. Chances are, when we first learned to play catch with baseball, we had problems. Your poor partner had to chase after first tentative throws, which never seemed to go where you wanted. But gradually, after a little bit of practice and several exhausted partners, you got better. Eventually, you could place the ball right onto your partner's gloves almost without conscious thought. In fact, expert pitchers don't think about how to throw; they simply concentrate on where to throw. Somehow, the brain calculates the precise path needed to deliver the ball to the desired location. Then it commands the arm to a predetermined release point and time with exactly the right amount of force. All this happens in a matter of seconds, without a thought given to the likes of Isaac Newton and the equations that describe the baseball motion. So what? You may wonder, why bother all the equations that describe why it travel and why it travels the way it travels. Unfortunately, to find a pitching machine for a batting cage or to launch spacecraft into orbit, we can't simply tell the machine or rocket to take aim and throw. In the case of rocket especially, we must carefully study its motion between launch pad and space. Now we'll define a system for analyzing all types of motion. It's called motion analysis process, MAP, checklists, and is shown in figure 4 to 6. And let me show you that figure. No, so in order to do a motion analysis process, first we define a coordinate system, derive an equation of motion, apply simplifying assumptions, assign initial conditions, perform error analysis, and then test the model. Now we'll define a system. Okay, we have already done that. To put the MAP into action, imagine that you must describe the motion of your baseball throw by two baseball players in a figure. Let's see. Let me show you the figure. Okay, so here we can see the thrower is throwing the ball at the receiver. First of all, you need to define some frame of reference, or first of all we need a frame of reference or coordinate system. For example, do you want to describe the motion with respect to a nearby building or to the center of the earth? In either case, you must define a reference point and a coordinate frame for the motion you are describing as shown in figure. Okay, next you need some shorthand way of describing this motion and its relation to the forces involved. A shorthand way we will call an equation of motion. Once you've determined what equation best describes the baseball motion, you need to simplify it so you can use it. After all, you don't want to try to deal with how the motion of the baseball changes due to gravitational pull of Venus or every little gust of wind in the park. So you must make some reasonable simplifying assumptions, like there is no air resistance, and though Earth is not a perfect sphere, that has got perturbations, but still we can ignore them safely for minimal analysis on the Earth. For instance, you could easily assume that the Earth attraction on the baseball from Venus, for example, is too small to worry about, and the drag on the baseball due to air resistance is insignificant. And in fact, as a good approximation, you could assume that the only force on the baseball comes from the Earth's gravity. The sun is also pulling the ball, the moon is also pulling the ball, but we only consider the Earth's gravity. With these assumptions made, you can then turn your attention to finer details of the baseball problem. For example, you want to carefully define where and how the motion of the baseball begins. We call these the initial conditions of the problem. If you vary these initial conditions somehow, you throw the baseball a little harder or a slightly different direction, the motion of the baseball will change. By assessing how these variations in initial conditions affect where the baseball goes, you can find out how sensitive the trajectory is to small changes in them. Finally, once you've completed all these steps, you should verify the entire process by testing the model of baseball motion you developed. Actually, throw some baseballs, measure their trajectory deviations, and analyze differences between the motion you predict for the baseball and what you find from your tests. Okay. Uh, so if you find significant differences, you may have to change your coordinate system, equations of motion, assumptions, initial conditions, or all of these. With mission analysis process, what was MAP? Mission analysis, mission motion analysis process. In mind, we begin our investigation of orbital motion in the next section by considering some fundamental laws of Isaac Newton. Okay, so Newton's law. Since the first cavemen threw a rock at a saber-toothed tiger, we have been intrigued by the study of motion in our quest to understand nature. We look for simple fundamental laws and all objects obey. These laws of motion would apply universally for everything from gumdrops to galaxies. They would be unbreakable and empower us to explain the motion of the heavens, understand the paths of the stars, and predict the future position of our Earth. In the next session, we have in the previous sessions we have seen how the Greek philosopher Aristotle defined concepts of orbital motion that held favor until challenged by such critical thinkers such as Galileo and Kepler. So no, okay, let's get to the crux. Reflecting on his Newton rightly observed that he stood short observations of principles of motion and inertia related to Kepler's law. Isaac Newton was poised to determine the basic laws of motion that revolutionized our understanding of the world. No single person has had as great impact on science as Isaac Newton. Yeah, we all agree on that. Though there were Islamic scholars that have done pioneering studies in orbital mechanics, astronomy, optics, and all of these things. Theology, mathematics, physics, chemistry, medicine, cartography, cryptography. His new and so coming back to Newton, his numerous discoveries and fundamental breakthroughs easily fill a volume the size of this book. Inventing calculus, math students still haven't forgiven him for that. Inventing the reflecting telescope and defining gravity are some of his many accomplishments. So, reflecting telescope was invented by Isaac Newton. For our purposes, we'll study the motion of orbits. Astrodynamics builds on four of Newton's laws, three of motion and one describing gravity. Okay, so let's study weight, mass, and inertia. Before plunging into a discussion of Newton's many laws, let's take a moment to complicate a topic that until now you probably thought you understood very well. Weight. When we order a quarter pounder with cheese, we're describing the weight of the hamburger before cooking. To measure the weight, say to determine what it weighs after cooking, we slap the burger on a scale and read the result. If a scale gave weight in metric units, we'd say our quarter pounder weighs about 1 newton. This property we call weight is really the result of another more basic property of the hamburger called mass plus the influence of gravity. Yeah, so weight is mass plus gravity. A hamburger that weighs 1 newton or one fourth of a pound has a mass of 1 by 9 point. So something that weighs 1 newton, if something is weighing 1 newton, its mass is its mass is 1 by 9.798, or approximately equal to 1 by 10 acceleration due to gravity. Knowing the mass of our hamburger, we automatically know three useful things about it, as illustrated. First, mass is the measure of how much matter or stuff the hamburger contains. The more mass, the more stuff. If we have a hull 200 quarter pounds to a family picnic, we can add the masses to individual burgers to determine how much total mass we need to carry. Carrying these hamburgers, which have a total mass of 22.5 kg, will take some planning. Thus, knowing how much stuff one object has is important whenever we combine it with other, as we do for space missions. But that's not all. Knowing the mass of an object also tells us how much inertia it has. Galileo first put forth the principle of inertia in terms of an object's tendency to stay at rest or in motion unless acted on by an external force. To visualize inertia, assume you are in couch potato mode in front of TV while you work sitting on the desk, calling for your attention. Someone just can't motivate yourself to get up from the couch and start working. You have too much inertia, so it takes an outside influence, another person, or deep rooted fear of failure to overcome that inertia, right? For a quantity of mass, inertia works in much the same way. An object at rest has certain amount of inertia represented by its mass that must be overcome to get in motion. Thus, to get the quarter pound from its package into your mouth, you must overcome its inherent inertia. To do that, you pick it up from, if you can. An object already in motion also has inertia by virtue of its mass. To change its direction or speed, we must apply a force. For instance, a car skating on ice slides in straight line indefinitely, assuming no friction, or at least until it hits something. Finally, knowing an object's mass reveals how it affects other objects merely by its presence. There is an old corny riddle that asks which weighs more, a pound of feathers or a pound of lead. Well, if it's a pound, then they weight the same, 1 pound. Yeah. Why is that? Weight is a result of two things: the amount of mass or stuff and gravity. So, assuming we measure the weight of feathers and lead at the same place, their masses are the same. Gravity is the tendency for the two chunks of stuffs to attract each other. The more stuff or more mass they have, the more they attract. This naturally attraction between chunks of stuff is always there. Thus, our quarter pounder lying in this package causes a very slight gravitational pull on our fries, milkshake, and all other masses in the universe. You'd better eat first. So even this mouse is having a gravitational attraction on this laptop, on my mic, on my earphones. Now that you'll never be able to look at a quarter pound the same way again, let's now see how Isaac Newton used this concept of mass to develop some basic laws of motion and gravity. Momentum. Newton's first law of motion was actually a variation on Galileo's concept of inertia. He discovered it and other principles of gravity and motions in 1655 when a great plague ravaged England and caused universities to close. At that time, he was 23-year-old student at Cambridge. Instead of hitting the beach for an extended spring break, the more scholarly Newton hit the apple orchard for meditation, and so legend has it. But his findings weren't published until 1687 in the Mathematical Principles of Natural Philosophy, in his monumental work, he stated Newton's first law of motion. A body continues in its state of rest or uniform motion in a straight line unless compelled to change that state by forces impressed upon it, moving in a straight line, not in a curved path. Because if it is moving in a curved path, then there is angular acceleration. Okay. Newton's first law says that any object or chunk of mass that is at rest will stay at rest forever unless some force makes it move. Similarly, any object in motion will stay in motion forever with a constant speed in the same straight line direction until some force changes its direction either by speed or direction of motion. Try to stop a speeding bullet like the one shown in a figure. You have it over here, and you'll get a good idea how profound Newton's first law is. One very important aspect of the first law to keep in mind, especially when you study spacecraft motion, is that motion tends to stay in straight line. Therefore, if you ever see something not moving in a straight line as a spacecraft in orbit, some force must be acting on it. Okay, as I already told you, we know that an object at rest is lazy. It doesn't want to start moving, and will resist movement to the fullest extent of its mass. We've also discovered that once it is in motion, it resists any changes in its speed or direction. But the amount of resistance for an object at rest and one in motion are not the same. This seemingly paradox is due to the concept of momentum. Momentum is the amount of resistance an object in motion has to change its speed or direction of motion. So, momentum, let's put it here, and momentum is the amount of resistance an object in motion has to change its speed or direction, aka velocity. Okay. This momentum is the result of combining an object's mass with its velocity. Because an object's velocity can be either linear or angular, there are two different types of momentum: linear momentum and angular momentum. Let's start with linear momentum. To see how it works, we consider the difference between a bulldozer and a baby carriage moving along a street as shown in the figure. Let me show you. I don't know why do they call bulldozer a bulldozer? Is it rousing a bull? Okay, bulldozer, baby carriage, and momentum of an object is the product of its mass and velocity. So a bulldozer moving at the same speed as the baby carriage has much more momentum due to its large mass. Okay, bulldozers are massive machines designed to savagely lift tons of dirt from earth. Baby carriages are delegated four-wheel cars designed to carry cute little babies around the neighborhood. Obviously, a bulldozer has much more mass than a baby carriage, but how does their momentum compare? So, if I can make a baby carriage go really fast, but it has got a small mass, I can still have the same momentum. Okay. Obviously, a bulldozer has much more mass than a baby carriage, but how does their momentum compare? Unlike inertia, what is the function only of an object's mass? Linear momentum is the product of object's mass and its velocity. Note, because we describe the velocity and momentum in terms of magnitude and direction, we treat them and other important concepts as vector quantities. So momentum is a vector quantity. Okay, so and it is described as, where is my pen, P equal to mv. Mass is a scalar quantity, where p is the linear momentum, kg meter per second. We get this SI unit, kg meter per second. uh, to compare the linear momentum, we constantly refer to the velocity vector as v vector, which denotes speed and direction. The magnitude of the velocity vector we call speed, or simply velocity v. Okay. To compare the linear momentum of a bulldozer and the baby carriage, we have to know how fast they are moving. For the two to have the same linear momentum, the baby carriage, being much less massive, would have to be going much faster. At the end of the section, we will show the relationship. Linear momentum is fairly basic because it involves motion in a straight line. Angular momentum, on the other hand, is slightly harder to understand because it deals with angular motion. Let's consider a simple toy setup. If we set the top upright on the table, it will fall over. But if we spin it fast enough, the top will seem to defy gravity. A spinning object tends to resist change in the direction of and the rate of spin, like the toy top shown in figure. For let me show you the figure. So see, some very basic principles of physics are being applied. If I just put the top on the table, it will fall, but if I spin it, give it an angular momentum, then, well, as we have already concluded that anything at rest would remain at rest, so our top at rest will tend to remain at rest. But if I spin uh, the top, it will tend to be spinning, and hence it is defying gravity. uh, let's consider a simple toy top. If we set up the top, it will fall, but if we spin it fast enough, the top will seem to defy gravity. A spinning object tends to resist change in the direction and rate of spin, like the toy top shown in the figure. Just as the object moving in a straight line resists changes to its speed and direction of motion. Angular momentum. Angular momentum is denoted by h. Is the amount of resistance of a spinning object to change in spin rate or direction. Okay. Angular momentum. Angular momentum is the amount of resistance of a spinning object to change in spin rate or direction of spin. Okay. Linear momentum is the product of the object's mass, which represents its inertia or tendency to resist a change in speed and direction, and its velocity v. Similarly, angular momentum is the product of an object's resistance to change in spin rate or direction, and its spin rate. The an object's resistance to spin is called moment of inertia. Okay. An object's resistance to spin. What is moment of inertia? What is moment of inertia? Mm, answer is an object's resistance to spin is its moment of moment of inertia. Okay. An object's and that will define by I. Okay, capital I, or let me write it over here. I. We represent the angular velocity, which is the vector omega. So we find the angular momentum vector h using equation h via vector equal to I into, so angular momentum is equal to moment of inertia This implies that angular momentum, let me turn it down a bit, angular momentum is equal to moment of inertia into angular velocity. Okay, so here is moment of inertia. So what do we get as the units? We get and this has to be find out by the right hand thumb rule. Okay, I'll show you a picture of right hand thumb rule. So angular momentum, let's come here, h vector, its unit is kg meter square per second, kg meter square per second. Inertia, it's kg meter square, kg meter square. And angular velocity is radian per seconds, is radians per seconds. So if we take kg meter square per second, there must also be a radian here, but okay, I'll try to figure it out. Where am I going wrong? Let's see the right hand thumb rule of angular momentum. Until then, we find the direction of angular velocity vector omega and the angular momentum h using the right hand thumb rule. Okay, like this. So in the direction, if we curl our fingers in the direction of the angular velocity, for example, let me give an example. For example, there is a top that is rotating in this direction. So if I put because this is a 2D screen, if I put my fingers curled around, so I see the thumb pointing towards me, so that is the direction of the angular momentum. To characterize the direction of angular momentum, we need to examine the angular velocity. Look at the spinning wheel. Look at the spinning wheel. Uh, in figure, we have already spin the spinning wheel and apply the right hand rule. With our fingers curled in the direction of its spinning, our thumb points in the direction of the angular velocity vector. Okay, angular velocity vector. Okay, and the angular momentum h, and that would be the direction of the angular momentum h. Okay, makes sense. Fair enough. So let's take a pause for some water break. Okay, so we are back. To characterize the direction of angular momentum, we need to examine the angular velocity. Looking at our spinning wheel in figure and applying the right hand rule with our fingers in the direction of the spinning, we will find the angular velocity and the angular momentum. So what that means is angular momentum is always in the same direction as the angular velocity vector. In the next section, we'll see that because of angular momentum, a spinning object resists the change to its spin direction and spin rate. Mhm. So we can describe angular momentum in another way. I've got three eyelashes. We can describe angular momentum in another way. A mass spinning on the end of a string also has angular momentum. Why is my mouse wobbling? Yeah, in this case, we find it by using the instantaneous tangential velocity of the spinning mass v vector and the length of the string r, also called the momentum. We combine the two of these with the mass using the cross product, and we see. Okay, let me show this to you with a figure. So see, we are spinning a ball in direction, and we have got an angular momentum, and this is the tangent arm which is connecting our hand, the thread, to the ball. Okay, so we can say uh, angular momentum at any given instant h is equal to r vector, which is the tangent arm, multiplied by mass into velocity vector. Okay, uh, by the nature of the cross product of operation, we can tell h must be perpendicular to both r vector and velocity vector. Once again, we can use this right hand rule to find h vector as shown in figure 4.6. 4.2 and analyzes the mass of the end of the string in more detail. We'll see that angular momentum is a very important property in spacecraft orbits. In chapter in subsequent of our lessons, we'll find angular momentum is also a useful property for gyroscopes and spacecrafts in determining and maintaining their attitude. Astro fun fact: spiraling football. Okay, why does a spiraling football go farther than a tumbling one? Spiraling football resists change to spin angular momentum direction, so it pretends its streamlined profile to the wind throughout its flight. This allows the ball to go farther than a tumbling ball, which encounters greater wind resistance. Thus, this same principle applies in a rifle barrel. Rifling, rifling refers to the spiral grooves cut inside a barrel. This causes the bullet to spin as it's fired, giving it angular momentum. The spin keeps the bullet from tumbling, thus making it less susceptible to wind resistance so that it can go farther and straighter. Changing momentum. Uh, okay, let's see. Okay, so that's a little bit of a long topic. So I guess we should stop here and we will continue from changing momentum in our next lesson. Okay. So that was all from my side today. I hope it was not that fun, I know, but hopefully it makes some concepts clear. Okay, thank you very much. Have a great day.